Okay, so, what we are looking for is this k n, which is SO 2 n intersection SP 2 n R, k n canonical form, okay, canonical forms of covariance matrix, right. So, this is what we are looking for. So, this canonical form does not necessarily mean that this has to be diagonal. Okay. So, the first form 1, which is a, which we considered like this G, which is our, so this is the real covariance matrix which we considered as half of S, such that S is a symplectic transformation, it is symmetric, and it is positive definite. Okay. So, this is the class that we first considered. Now, what we look for is canonical form for generic element of this, okay, under this k n transformation. That is what we are looking for. Okay. And yes. So, what you can start with, let us say I take these S belonging to SP to an R, such that S is equal to S transpose, which is symmetric. So, this means that if I write S in this form S3, where this S1, S2, S3, these are n cross n real matrices, and of course, S1, I mean, yeah, this has to be positive, okay, because S is positive. So, S1 is positive, S3 is also positive as S is positive, okay. And then I mean, of course, this S1 is equal to S1 transpose and S3 is equal to S3 transpose. Of course, that is true because it is symmetric. So, this tells me that it requires for each of them, because of the symmetry, it requires n into n plus 1 real parameters, right, to describe them, right. For this it is n into n plus 1 by 2, for this n into n plus by 2. So, therefore, in total n into n plus 1 real parameters to describe this S1 and S3. Now, what about S2? So, for S2, you know that you will have to satisfy this condition that S omega S transpose is equal to omega, right. So, if you do that, you will have S1, S2, S2 transpose, S3, then this is 0 identity minus identity 0, then this is S1 because S1 transpose is S1, then transpose of this is S2, S2 transpose S3 because transpose of S3 is equal to this thing. So, this should be equal to 0 identity minus identity 0. So, from here you can figure out that you do not need any extra parameter. Okay. So, once you specify this S1 and S3, you can also figure out what will be S2. Okay. So, you do not need extra parameter for that. Okay. So, in particular you can figure out what is S2 square, and then you can apply this relation which will also tell you what will be S2. Okay. So, this means that this set, that means this kind of covariance matrices, okay, I have not yet proved whether this is a valid covariance matrix or not, but this is parameterized by n into n plus 1 real parameters, right. Okay. Because once you fix S1 and S3, S2 is automatically fixed through this relation. Okay. Right. So, therefore, this class is parameterized by n into n plus 1 real parameters, and now the question is that okay. So, this is something which one can prove. So, what is it that I will have to prove in order that this is a valid covariance matrix? This is positive definite symmetric, right, 2n cross 2n matrix. What else we need to prove? We need to prove that gamma r plus iota by 2 omega is greater than equal to 0, right. This is exactly what we need to prove, so that it can become a covariance matrix, right. Okay. So, therefore, if you take gamma r as half of S, this boils down to S plus iota omega greater than equal to 0, right. Okay. Right. And so, now what we already know that S is positive, right. This is given, S is positive. So, we need to show that S plus I omega is also positive if S is positive, right, and that is simple. So, okay. So, how will you do that? Let me, yeah. So, let me write down, maybe I will just erase this part. So, this is my S. Okay. So, S plus iota omega, if I know what is omega, this is basically S1, S2 plus iota identity, S2 transpose minus iota identity, S3. Okay. So, this is how you will have, right, because omega. So, now you have to prove that this is positive definite, I mean positive semi definite, sorry. Okay. So, let us take this vector, any vector you can take. Let us take this vector x1, x2, xn, then p1, p2, pn. This is a real vector. Okay. So, this belongs to R2n. Okay. So, what you do is you take R transpose S plus I omega R to show its positivity. Okay. So, if you do that, what you will get is the following. This is basically R transpose S R, I mean because of this thing, and then plus iota, this is X transpose P. Now, what I am calling X transpose, I will tell you, minus X transpose P transpose. What is X? X is, this one is X and this one is P. Okay. So, if I calculate this with this form of omega, what you will get is this one. Now, see, these two are same because these are real, because this is scalar, this is also same real number scalar. So, basically this will vanish, right. So, what you have is this one R is R transpose, and this is of course positive because positivity of S, right. So, this tells you that S plus iota omega is also positive definite, and so this gamma r. So, basically gamma r is equal to half of S, this is a valid covariance matrix, right. Okay. Right. And you know that this half identity 2n cross 2n, this is of course an element of this one, right. So, and this corresponds to the covariance matrix of, this is the covariance matrix of this one. You have n mode. So, alpha 1 coherent state, alpha n. Okay. So, this is the n mode coherent state. Okay. Which is of course a Gaussian state. Okay, good. So, yeah. Good. Okay then. So, this is basically the classification. This is the class of this is one class of course, and okay. Now, the question is that can we diagonalize such an S? Okay, that is the question. Can you diagonalize it? Okay. Now, of course, this is symmetric, and therefore, there will be a rotation matrix. Let me call it as SO2n, under which this R half S R transpose, it will be diagonal, right. Maybe it is called lambda 1, lambda 2, lambda 2n, and these are all positive. This can always be done. Problem is that we need, this is not just in this one. So, basically what we need is sp2n comma r, right. So, that is something which we need to figure out, that whether this can be done. Okay. And yeah, so here actually I need some other parameterization of this S, because that will help us to parameterize. So, basically what we are looking for is, you remember these elements are of this form, this R is of this form, S are x y, right, which is x, y, minus y and x, right, which satisfy a certain condition. So, what we need to show is that with respect to this kind of matrices elements, we can diagonalize each such S. Okay. Okay, good. So, actually I will just use this result without proving, because we do not have much time to prove it. So, what I will do is, so if I take S within SP 2 n R such that S is equal to S transpose and S is positive, right. Then I can write this S, as I said, I can of course write it as S1, S2, S2 transpose S3 with this S1 is equal to S1 transpose is positive, S3 is equal to S3 transpose which is positive because of the positivity of that, but we need more. So, what one can do is one can write it as S of U and V, which is U inverse, then it is minus, this is U V, this is minus V U, this is U plus V U inverse V. Okay, so, what are these? So, U and V, these are n cross n real matrices. Okay. And U is equal to U transpose which is positive, V is equal to V transpose. So, you see that these two conditions together will tell you this is n into n plus 1 parameters. Okay. This symmetry condition, right. And you see that if I take this as S1, of course, U is positive. So, U inverse is positive. I can take this S2, then S2 transpose, which should be this one, S2 transpose. So, S2 transpose is minus V transpose U transpose, and V transpose is V, U transpose is U. So, this is S2 transpose. Okay. And S3 is again, you see that because U is positive, right, U is positive, and this is a similarity transformation, V U inverse V is V U inverse V transpose, because V is, so this is a similarity transformation. So, therefore, this is also positive, right, this matrix is positive, this is also positive. So, therefore, as a whole this should be positive. So, this is my S3, this is also positive. Okay. So, one thing what one should, so this is n into n plus 1 parameter, no doubt of it. One thing what one should figure out is that this S U V is indeed an element of SP2NR. So, that should be verified, to verify. Okay. Because otherwise, I cannot claim that this is an element of, so this should be an element of this class SG. Okay. So, this is what one needs to verify, that yes, indeed this is an element of SP2NR. Okay. So, yeah, so this is what we basically we need to verify it. So, my suggestion is that this should be valid, that this is, so therefore, what point is S U V sigma S U V transpose, it should be equal to omega, this is the thing, it should be valid. Okay. So, that one should verify. One can try to see how to do that. Okay. So, anyway, so the question is that this actually can be diagonalized. So, S U V, again I am not giving the proof, this can be diagonalized using some R which is S R of x y belonging to K n. What does it mean? It means that your S of U V is equal to R transpose some diagonal matrix R. Okay. and what one can prove is that, okay, so this is fine, this we can always do, but what is this lambda? So, this is some diagonal matrix, right. So, what you can prove is that this is something interesting, that this will have eigenvalues, of course, let us say, and these are positive, right, because this is a positive definite matrix. So, S1 square, S2 square, Sn square, this is fine. Now, this one is interesting. So, next n eigenvalues are not arbitrary, they are S1 1 by S1 square, 1 by S2 square, 1 by Sn square. Okay. So, basically it tells you that this matrix can be diagonalized by using elements of this type. Okay. Right. So, what does it mean? It means that if I take this x y minus y x is transpose, and then this one u inverse, sorry, I will have to take here this one. So, u inverse minus u v minus v u plus v u inverse v, and then x y minus y x is transpose. This should be something like this lambda. Okay. So, this is what one can manage to prove. Of course, you have this condition that x transpose plus y transpose is equal to identity, and I think x y transpose is equal to x y transpose to the, because this is an element of K n. Okay. So, this is something which one can prove. Again, I am not going into the proof of this. If time permits later, I can do that, because this is otherwise it will go on. So, what my plan is to finish this work today, so that next Friday I can start this Gaussian states, etc. I mean, this should be just a simple matrix calculation, nothing more, nothing less. So, the interesting thing is this one. Yes. No, Williamson's theorem takes care of arbitrary symplectic transformation.
Okay, so there is like this is a special kind of symplectic transformation, but if you go to like if you have other symplectic transformations also, then you can bring it into that.
Yes, doubly degenerate one. Yes, yes, yes. So, because here this you do not have this full freedom of using this Williamson's theorem. Okay. But still this is interesting, that why should it be like this thing, this kind of thing.
Okay. So, the symplectic transformation that diagonalizes is not unique, there are others also, but there exists one symplectic transformation that will bring it into a
exactly, and this is the, basically this is what, this is a I mean the eigenvalue of this is 1, right.
The determinant.
Sorry, determinant of this is 1, right. Yeah. So, but is it that this determinant, oh, we will have to calculate basically. So, this determinant should be also 1, because you have used these rotation matrices. Okay. So, yeah, so that has to be the case. So, they they appear in reciprocal form. Okay, which is kind of also squeezing, right, quadratic squeezing, because this is S1 square, this is 1 upon S1 square. Okay, good. So, yeah, so I will not go into further details. So, this is what we assume that this will be the case. Okay. So, anyway, so therefore, you see that for this class which I defined earlier, there is a canonical form which is this one. Okay. Right. and of course, all of them are positive because S is itself positive. So, all of them are positive, right. And you see this is definitely squeezed. Why? Because if I assume, so it is true that not all of them can be greater than equal to half, right, except for one case. I mean of course, not half, one, because I will have to take half of this thing. Okay. So, not all of them equal to 1 except for the case when this is identity in the coherent state case. So, otherwise some of them will be greater than 1, some of them will be less than 1. So, therefore, it is definitely squeezed, the covariance matrix. Okay. So, only when it is a coherent state the squeezing does not happen. Okay. Okay, so let us look for this. So, first family is gamma g, second family which I call not gamma, this is S g and S h. Okay. So, let me again write down what is by the way, you can, so this is basically gamma r which is half S such that S is sp2 nr, S is equal to S transpose and S is positive. So, what you can do, you can multiply each element by some scalar quantity, let us say lambda. So, lambda gamma r. Okay. This is also a, where lambda is of course, you will have to take lambda greater than equal to 1, some real number. So, then you see this is also a valid covariance matrix, right, because it satisfies all the conditions. So, therefore, you can extend this to n into n plus 1 parameter, right, because of this. So, this is this parameter. Okay. So, now let us look at the second family. So, the second family is this one. So, this is again gamma r is equal to, this consists of this kind of covariance matrices C minus D, D and C, such that this matrix which you form by C plus iota D, which is H dagger and which you take greater than equal to half. Okay. C and D are n by n cross n real matrices. Okay. So, this is my, I mean I will have to prove that this is a covariance matrix, and yes. So, okay. What, so when can it happen? Basically C has to be equal to C has to be symmetric and D has to be antisymmetric, right. Yeah, this has to be the case. Okay, good. So, so you see that each such element, each such so called covariance matrix is determined by this Hermitian operator which is greater than or equal to half, right. Because once I give you the Hermitian operator, you can figure out this and vice versa, right. Okay. What more we need is that this has to be positive, this gamma r has to be positive, okay, which is of course this will again satisfy this, so the hermiticity anyway. So, this we will see now. One can figure out that the complex form of C. So, complex form means J gamma r and J dagger where this J is 1 upon root 2, this is n cross n, this is iota n cross n, this is iota n cross n, this is minus iota identity n cross n. So, this is your complex version. So, if you do all these things, what you will get is this one H 0, this is n cross n, this is n cross n, this is also 0 n cross n, and this is H star, not dagger, H star. Okay. So, this is what you will get. Okay. So, I think we discussed this form of this gamma C, which is of this form A, B, B star and A star, okay, where A has to be Hermitian and B has to be symmetric. Okay. So, this is the complex version. So, you see that this is of course in this form where A is your H, which is of course Hermitian, and B is 0, right. Okay. And so we discussed last time that when I take the complex, so when R goes to SR of this one, which is R prime, I mean you should put a hat here, okay. Then the corresponding complex version, it will go to a C R hat C, which I will call R hat C prime, where this SC is basically, because this SR is of course the SR of x y, which is an element of Kn, because that is what we are looking for. So, then SC it will be this, we discussed I think last time, 0 0 u star, where this u x minus I y, this is an element of this un. Okay. So, this is your SC, and so now you apply this gamma C, which is this one, and let us say it goes to, so this SC I will call SC of u because of this u. Okay. So, this will go to SC of u, then gamma C, then SC of u dagger. Okay. So, now you put all these things. So, SC is u 0 0 u star, then gamma C is H 0 0 H star, and then this dagger is u dagger 0 0, this is u transpose. Okay. So, if you do that, what you will get is this one u H u dagger 0 0 u star H star u transpose, okay, which is basically u star of this, okay, right. So, this is where it will go. So, this is your gamma C prime. Okay. Right. Now, I can always choose a unitary because this is unitary. I can always choose a unitary, so that this, because H is a Hermitian one, right, because of my condition H is Hermitian, and of course H is positive because it is greater than half. So therefore I can always choose unitary, so that this is diagonal, right, and this I can write is at lambda 1, lambda 2, lambda n, and which is also positive. In fact, it has to be greater than or equal to half, but that is okay, it is positive, and therefore this is also diagonal, right. Okay. In fact, these and these will be same because these are real, okay. Right. So you see that given this form, you can go to its complex version, and then you can use this symplectic transformation corresponding to this unitary, which will take it to a diagonal form, right. Okay. And now what you can do is, this is your gamma c prime. So now what you can do is, you can write the corresponding gamma r prime also, okay. So gamma r prime, you remember what was this relation between, so this gamma c is equal to j, was it j or something, gamma r j dagger, was it that or something else? What was the relation, j or j, right? Yeah, so you can invert this because j is invertible, okay. I mean j is equal to, j is unitary, j inverse is equal to j dagger, right. So therefore from there, if you write down this form, which is your V1 prime, V2 prime, V2 prime transpose V3 prime, and you can connect it, because this is your, this should be your A prime, B prime, B prime star, A prime star. This is the complex version, and then we know there is a 1-to-1 correspondence between this A prime, B prime and V1, V2, V3, etc. right. That I think we have done earlier. So anyway, I am not doing that. So basically what you will get is a form like this. If you do it properly, you will see that this will become diagonal of something like this, kappa 1, kappa 2, kappa n, again kappa 1, kappa 2, kappa n. Okay. And this happens because basically these two are same, this A prime and these are same, and B prime is 0. So from there you can figure out that this is the actual form. Okay. I mean, there is this relation, maybe I don't know whether I have written it, but anyway, this is simple, one can write it. Anyway, I am not. So this is a basically 1-to-1 relation is there. Yeah. So therefore you see that this is actually in the in this Williamson's form. Okay. And this is the diagonal form of, and now you can prove, because this is greater than or equal to half, so you can prove that this is indeed a covariance space. So basically what you can prove, that gamma r plus iota by 2, this is greater than or equal to 0, that also one can prove. I am not going to prove, but you can prove it. Okay. Right. So therefore you see, and this basically this tells you that kappa j is greater than or equal to half for all j. So this means that squeezing is not happening here, at least directly it is not happening. Yes, yes. Okay, good. So, and also you see that this matrix half identity 2n cross 2n, this is an element of this, isn't it? Yeah. and so how many parameters you will require? So, C is they are all symmetric, right. So, yeah, C has to be symmetric and D is antisymmetric. Okay. So, therefore, how many real parameters you will require? For C symmetric means n into n plus 1 by 2, right, and D antisymmetric means n into n minus 1 by 2, right. So, plus n into n minus 1 by 2. So, this is as a whole what? N square, yes. So, you need these many parameters. And one more thing one can prove is that between these two classes, okay, there is this class and here we have this class. The only common element is this one. Because you see, for this class squeezing is mandatory except for this element, whereas for this class no squeezing happens. So, this is the only common element between these two classes. Okay. Okay, good. So, therefore, these two are basically special subfamilies of covariance matrices, Kn invariant. I mean, you have to look, I mean, the Kn canonical forms you are looking for that. Now, let us look for the final one. So, you see that yes, this Williamson's theorem will require a generic symplectic transformation to bring it bring any a covariance matrix into this canonical form where you have double degeneracy, right. But this particular family, this S of H, actually brings it brings these its covariance, its element into the Williamson's form, okay, using of course elements from Kn, not outside of that. Okay. So, let us take this third family, which is S of K. K is this, this group Kn. And what is this? This is as usual, we are looking for these covariance matrices. So, the set of all covariance matrices, I will call this as set of all bona fide 2n cross 2n covariance matrices. Okay. This is the set. So, this is an element of this set such that R transpose gamma R is equal to some diagonal matrix for some R belonging to Kn, right. This is what we are looking for. So, it should be made diagonalizable by using some element of Kn. So, this is the definition. Right. So, this R transpose gamma R, which is a diagonal matrix. So, this is my gamma r prime, right. So, this will be, of course, my standard form is V 1, V 2, V 2 transpose V 3. So, here you see that V 1 is diagonal, V 2 is 0, V 2 transpose is 0 and V 3 is diagonal, right, because this is diagonal, okay, right. And this tells you equivalently you can say that gamma c prime, which is of course of this form A, B, B star, A star, and this will be basically, if you do the calculation, it will be half V 1 plus V 3, which is again diagonal because those both of them are diagonal. B is equal to half V 1 minus V 3, which is again diagonal, and then B star, this is all real, okay. So, these are all real. So, B star is equal to B and A star is equal to A. Okay, so, this is what you will have, because these are all real matrices. This is all real because it is diagonal, so it has to be real. This is also real n by n matrices. Okay, good. So, this can be cast in again some canonical form, and so what the result tells me is that the so let me first write down this result. So, this is the theorem. The Kn canonical form of a, so when I say Kn canonical form means after applying this kind of transformation, okay, which are elements from Kn. So, this covariance matrix gamma r belonging to S, which is the set of all covariance matrix. So, the Kn canonical form of a covariance matrix is diagonal. That means, this is a diagonal matrix, okay. This is diagonal if and only if its complex form gamma c, which is basically of this form A, B, B star, A star, has blocks A and B such that AB is equal to B A star. And now we know that here, because in this case we know, because this is a covariance matrix. So, A is equal to A dagger and B is equal to B transpose, okay, because this is a covariance matrix. So, then you can show that this is actually A B whole transpose, okay, because B transpose is equal to B and A transpose is equal to A star. Okay. So, therefore, you see that this Kn canonical form of a covariance matrix, it will be diagonal if and only if these block matrices in its complex version satisfy this condition. Okay. Okay. So, once again I will not go into the proof of this proof is there in this paper. Okay. So, basically what you need to do is you can first assume that so this is Hermitian. So, you can diagonalize it with some unitary. So, U1A U1 dagger is equal to some diagonal matrix, okay. and this has to be positive because of this condition. So, some diagonal one, let us say this is A1, A2, etc., AN, and this has to be positive because this corresponds to the covariance matrix. So, this has to be positive. Okay. Now, one possibility is that this is non-degenerate. Okay. All of them are different. So, then the proof is simple. Basically, if you so basically this is the transformation that will bring it into the diagonal form. So, of course, this can always be done because this is Hermitian A dagger, A is equal to A dagger, and the same one when you apply on this B, basically you can look at this U1 B U1 transpose, the corresponding action. So, this condition will demand that this one is also diagonal, and then it is like like something like maybe some B1, B2, etc., Bn. These are not necessarily real number because B is not real. Okay. So, these are not, and this unitary may or may not bring this B into a form where all these are basically what you are asking is whether they are eigenvalues, which is not necessarily the case. Okay. Because this U1 is chosen for A to bring it diagonal. I mean, why should it also make B to be to have eigenvalues? So, these are not eigenvalues. So, maybe what you can do is I can replace it by e to the power I phi 1, B2 e to the power I phi 2, so on, Bn e to the power I phi n, where these Bj's are all non-negative because I have made it diagonal, but it can have some phases. Okay. Because you see, this is what? This is what was the condition on B? B is equal to B transpose, right? A is equal to A dagger and B is equal to B. So, B is symmetric. In general, B is a complex matrix. Now, the unitary that I am using to make A diagonal, why should it make B also diagonal in the sense that all these are eigenvalues of B. Okay. So, if I see, this is a complex symmetric matrix. Okay. So, the point is generally it will not even bring it into diagonal form.
Then it's fine, but if it's coming to the diagonal form, then it has to be eigenvalue.
Yes, but yeah, eigenvalue means yes. So, these are this. So, you will have to have some phases. This is a complex matrix. Okay. But the point is why this has to be the form? Because of this condition. So, this is diagonal, and if you impose this diagonal condition here, then it will automatically make this to be diagonal.
But now those are eigenvalues.
Those are eigenvalues. Yes, those are eigenvalues. So, what we have assumed here, these are non-degenerate. Okay. So, therefore, you see that with this form, now this is not the final one. What you can now perform is you can now perform another unitary U2, which is of this form. Let us say plus minus e to the power maybe minus I phi 1 by 2 plus minus e to the power minus I phi 2 by 2, so on, plus minus e to the power minus I phi n by 2. Okay. So, if I now apply this U2 on, let us say I call it as A prime and this I call B prime. Okay. So, if I now apply this U2 on A prime, U2 dagger, you will see that nothing will change in A prime because I have chosen U2 in this form. Yes. So, nothing will change. But now, if I apply U2 B prime U2 transpose, because that is how B prime gets transformed. So, what you will see is that it will now become diagonal like B 1, B 2, etc., B n, okay, and all these are non-negative. Okay. So, basically if you so if you apply this AC, the complex version of the symplectic transformation, which corresponds to U, which is U2 U1, then this will bring this covariance matrix satisfying this condition into a diagonal form. Okay. And basically, if I now look at this gamma C, let us say this is my this, let me call it as A double prime, and this I call as B double prime, and corresponding this one let us say gamma C double prime, okay, and then the corresponding gamma R double prime, which is the real part. So, what you will see is that this is something like, I do not know whether you will have half factor or so, one can figure out. This is diagonal of something like this, okay, A1 plus B1, A2 plus B2, AN plus BN, and then A1 minus B1, A2 minus B2, so on, AN minus BN. Okay. And because this is a covariance matrix and all that, so basically what you can basically AJ is greater than BJ is greater than equal to 0. Okay. So, this is the diagonal form ultimately you will get, and this is not generically your in the Williamson's form. Rather, you can say that this is of the following form, which is so let me see, which is of so what you can do is you can again apply this squeezing transformation, etc. So that now basically this you can think of as diagonal of this form, S1 square kappa 1, S2 square kappa 2, so on, Sn square kappa n, and then this is kappa 1 by S1 square, kappa 2 by S2 square, kappa n by Sn square. So, this I can always bring this into this form. Okay. Why? Because these two are in general different, A1 B1, A1 plus B1 and A1 minus B1. So, I can in general take it in this form. So, now you can say that look, now I can provide individual squeezing to bring it into this form, diagonal kappa 1, kappa 2, kappa n, then kappa 1, kappa 2, kappa n, right. So, again this is a kind of this I mean this Williamson's form. Okay. Right. So, you see that therefore, this class of covariance matrices can be cast using these Kn operators into a canonical form which is diagonal, and yeah, so therefore okay, right, and this family, if we look at this family, this is more general than SG and SH. For SG, you will have to take this individual S to be, so for this Sj has to be 1, then it is of this Sg canonical form, right, kappa 1, kappa 2, kappa n, again kappa 1, kappa 2, kappa n.
Right. But for SG we had S1 square, S2 square, and so on till S1 by 1 by.
No, no, sorry, not S1. Kappa j is equal to half. Okay, yes. Okay, and for this you will have Sj is equal to 1. Okay, right? Yeah. So this is what you will have. Okay, good. So this is basically about this family, and so when I say that an element of this family can be cast into a diagonal form, okay, so you will have to satisfy this condition, and this is a very stringent condition, not always it holds good. Okay. So I will give you this example where you will see that, you know, so let us take this covariance matrix gamma r is equal to this is your V1, which is A 0 0 A, this is your V2, which is 0 C minus C 0, these are all real. This is V2 transpose, which is 0 minus C C 0, and V3, this is equal to B 0 0 B. Okay. So A and B has to be positive, and then your gamma r plus I by 2 omega has to be greater than or equal to 0, and this corresponds to, I think, AB minus C square is greater than or equal to 1. So this is the uncertainty relation. Okay. So okay, so this is so therefore now this is a valid covariance matrix and all that. Okay. So now if I now figure out, if I now so now you can figure out what is your gamma c, which is A B B star A star, okay, which is basically your J gamma r J dagger. Okay. So what you can see is that now you demand, so you demand that AB is equal to AB transpose. So this is what? This means that anyway you will have to figure out what is A and B, okay, from there. So one can in principle figure out. So basically what you will have is this one. So this will tell you that A is equal to B. Okay. So one can figure out what is capital A, capital B. So you see that in order that this covariance matrix can be cast into a diagonal form under this Kn transformation, is that you will have to satisfy this condition, otherwise it will not hold good. Okay. So now it may happen that for some covariance matrix you cannot have this thing. Okay. Like when we talk about this non-symmetric, so this can be a covariance matrix of a two-mode Gaussian state, and this, if A is not equal to B, then this is actually non-symmetric covariance matrix, okay, non-symmetric Gaussian state. So, it may happen that you cannot have this condition A is equal to B, and in that case you cannot diagonalize this thing using these Kn transformations. You can diagonalize it by using some symplectic transformation outside of Kn, but not within Kn. Okay. So, if I have this condition that A is not equal to B for some reason, then you cannot diagonalize it using Kn transformations.
It's still in that SG, right?
Is it in SG?
No.
No, this is a more general form. Okay. This, I mean, this is
Okay, it's in SK only if
yeah,
this
condition is satisfied, and that demands that A must be equal to B. I mean, one can figure out what is but this I think I mentioned earlier that the relation between A, B and this V1, V2, V3. Yeah, so that you can figure out and see. Okay. So, so therefore, this so if I only concentrate on symplectic transformation from this Kn, then of course sometimes I can diagonalize, sometimes I cannot. Okay, right. Okay, good. So then the fully general one is this one. Which is S. So, this is the R is a bona fide 2n cross 2n covariance matrix. Okay. So, this is the set. Now, of course, not every element of this set can be made diagonalized using transformations from Kn. It is not possible, right? But one can still talk about canonical forms of elements of S under Kn transformations. Okay, which need not be diagonal, but sometimes it can be useful. Okay. So, let us take gamma r corresponding gamma c, which is basically A, B, B star, A star, and where we know that A is equal to A dagger, which has to be positive, and B is equal to B transpose. Okay, this we know, right? Okay. So, now you choose some unitary U1 belonging to Un, because these are n by n matrices, such that this this U1 A U1 dagger, this is diagonal. So, let us say this is lambda 1, lambda 2, lambda n, and these are all positive because of this thing. This I can always do, right? Okay. So, then under such unitary, so when I say unitary means basically what you need to look at is this SC U1, right? under which what will be the corresponding transformation. So, this will take gamma c into this gamma c S c u1 dagger. Okay. So, this is what I am talking about, and this will be here, this will be u1 a u1 dagger, this is u1 b u1 transpose, then star of this u1 b u1 transpose star, and star of this u1 a u1 dagger star. This is what you will have. Okay, right. So, this is diagonal. Okay. But this we do not know whether this will be diagonal or not, okay, because here we do not know whether A B is equal to A B transpose. This we do not know. In the case of Kn, this set Sk, we know that, but here this is not the case. Okay, right. And in it does not have also any specific form. Okay, right. So, but you know what you can do is but this is, you know, this is basically, if you look at, this is a complex matrix. B is complex matrix, so this is also complex matrix. But what you can figure out that U1 transpose, so this is your U1 B transpose U1 transpose, and because B transpose is B, so this is U1 transpose, right. Okay. So, this means that this is complex symmetric matrix. This is diagonal and this is complex symmetric matrix. Okay. Right. So, because this is complex symmetric matrix, you know, of course, it will have, if I look at its diagonal entries. So, you know, one can use this property that this is diagonal and this is complex symmetric. Then what you can prove from here is that, so let us say this is my gamma c prime, okay, and now I go to the corresponding gamma r prime, the real version. So, here you can show that in this case what happens is this, so which is of this form. Okay. So, now what you can do is yeah. So, now let us look at this U1 B U1 transpose its diagonal entries. This is a complex symmetric matrix, right. So, I look at its diagonal entries and let us say it will have you know, something like this. It will have some phases, like, you know, maybe something like this. What can I say? Like Bj e to the power I phi j. So, where Bj's are greater than or equal to 0. This I can always do. Okay. So, now what you do is you basically take this next unitary is the following. So, yeah. So, what you do now, you choose another unitary, this was U1, which is diagonal, like plus minus e to the power minus I phi 1 by 2 plus minus e to the power minus I phi 2 by 2, what we have done earlier, plus minus e to the power minus I phi n by 2. Okay. Now, if I apply this U2, this one U1 A U1 dagger U2 dagger, this will remain same as U1 A U1 dagger, because this is diagonal. But now if I apply this U2, U1 B U1 transpose, then U2 transpose, what will happen to this? Here you see that it will have its diagonal entries without these phases, right. Yeah. So, yeah. So, these are basically non-negative numbers for all j, because this will have without the phases. Okay. So, effectively if you apply this SCU, which is U2 U1, then you will have this gamma r, which is so this is prime, then you apply this one, so double prime, which is what you get after applying this U, which is U2 U1 on gamma r. So, this you see that this will be of this form V1 double prime, V2 double prime, V2 double prime transpose and V3 double prime. Okay. So, in this case I do not have the full diagonal form, but what you have is the following, because this is, so what you will have is this one V1 double prime plus V3 double prime, this is diagonal. Okay. So, this I can do, and then V2 double prime transpose is equal to, anyway this is basically it tells you that this is symmetric, and you do not have to write like this, this is symmetric. Okay. This I can do, and then yes. So, in fact, I can make also these V2, this one, this V2 transpose JJ, these I can make actually 0. So, anyway, so this we will have to choose this U1 and U2 in such a way that this happens. So, you see that basically it tells you that in this format this is the thing, and then the diagonal entries of this V2 are all 0, and this is V1 double prime plus V3 double prime is diagonal. I am not saying V1 double prime is individually diagonal, V3 double prime is individually diagonal. If I add them, then this is, it is diagonal. So, this is, you know, if you remember this example, this is A 0 0 A, then 0 C minus C 0, then 0 minus C C 0, then B 0 0 B. It is something of this form, okay, because the diagonals are 0, and in this case of course both of them are diagonal, that is okay, but this is a special case of that form. So, the point is that if I take a generic covariance matrix under this Kn transformation, it will not, it cannot be brought into a diagonal form, but it can be of this form, where this one plus this one is diagonal, this is symmetric, and its diagonal entries are all 0. Okay. So, this is a canonical form that you can have by using these Kn transformations. Okay. There is another canonical form which anyway I am not going to talk about, this is more complicated one. So, when it will be required for describing this Gaussian state entanglement, maybe I will talk about that. So, this paper talks about this particular canonical form for the most general case, and there is another canonical form which is slightly simpler, which is basically you have only diagonal entries here, and this is I mean something like this is also diagonal, this is also diagonal. So, So, that so which is again of this form? No, it is not of this form, this is a something different. Yes. So, what I am saying, you will have a form like this. This is lambda 1, lambda 2, lambda 2n. Here you have another diagonal, here you have another diagonal, everything else is 0. Okay. So, this is also a canonical form that one can bring using this Kn transformation. So, what therefore, so we know what happens to S of G, which is of course in a diagonal form, S of H again diagonal form, S of K again diagonal form, but S it is in general not in diagonal form under this Kn transformation. But that does not mean that we cannot use it, we will use it. Okay. These forms will use it, and but these are canonical forms. This is the best that we can do with these Kn transformations. Okay. Yeah, I think this is all. So, I will stop here.